Yeah. So typically, uh, yeah. So let's say this is your any power electronic converter, and let's say it may be having a motor load, or it may be having any other kind of load. Now, so typically when we see that we have given a DC input, so current will flow to this positive terminal, and eventually it will go to inside the converter to the load, and then it will come back. So this is how typically the path looks like, right? But sometimes what happens is that you know how a capacitor is defined. Capacitor is nothing but two parallel plates, right? Two parallel conducting plates separated by some dielectric material like air. So now take an example of some load like maybe a fan, or sometimes like any other motor, or let's say a CPU. So there are a lot of metallic loads, right? So loads basically having a metallic body. Similarly, you may have a source which can also have metallic body or conducting path, right? Now, this is physically the earth, the ground, physically earth, okay? So in between, you can see this is also a conducting medium for us, and this negative force potential, or this metallic body of the load, or the negative conducting path. So sometimes that creates an parasitic capacitor. These are not capacitors which we added deliberately. This comes into picture unwanted, in an unwanted fashion. So we call it parasitic capacitance. Sometimes people call it leakage current path. So what happens is that since we are doing a lot of high frequency switching, this capacitor, you know, capacitance XC is 1 by 2 pi FC, right? So the capacitive impedance is given by 1 by 2 pi FC. Now when we do high frequency switching, like as I told in our power electronic converter, generally we do at least kilohertz level switching, sometimes hundreds of kilohertz. So then with high frequency, so basically F increases, this XC goes down, so impedance goes down. So it provides a parallel or additional path. So current due to this capacitor, this unwanted or parasitic capacitor, this can flow through this route. It can also flow through this outer route. Okay, so there are basically two paths it will have. Through the negative bus, also it can flow through the positive bus. So this kind of phenomena actually gives rise to common mode behavior, because it is common to both the lines. Whereas in a differential mode, what will happen? Current will go like this and eventually come like this. That is the differential mode. And common mode is something which will go like this and go like this through an external medium. Okay. So more detail about is this out of scope now. If time permits, we'll discuss it in the motor controller class. But I believe you got some idea about it. Now coming back for today's topic, today we are going to focus on electric motors, but just a quick reminder about the power electronics session that we were following. So for power electronics, right, of course there are huge number of converters that are used in power electronics, but the most important ones which are used in electric vehicles or very relevant, a summary of them I have provided in a document which is given in this second. This you can let me go slowly. This study material I have already shared with you earlier. So in this power electronics folder, there is a main study material subfolder, inside which there are two class materials. One is what we were following in more detail, and then there is a kind of compressed version where I summarized several important concepts. What are the different types of converter, buck converter as an example, right? What is PWM? What is closed loop control? So those things are, I try to summarize in a single small document so that you can quickly refer to the important points, right? So buck converter we studied slightly in more details, and then there are so many other converters also. Of course, as I told, power electronics is the entire semester long course, right? We cannot study each and everything in detail. That's the reason I provided you a summary so that you can quickly refer to the important topics. And some of these topics we are going to study in motor controller also, right? For example, DC to AC converter we are going to study in the motor controller section. Similarly, some AC to DC converter you are going to study in the rectifier section. So that's the reason those converters are not discussed more in details. But then a summary of them I have provided in this document. So please go through them in your free time. Okay. Today what we are going to do, we are starting with the motors because this is also a very important topic in electric vehicle segment. So for this motor topic, we are going to follow the study material provided by IntelliPART team. Okay, and this study material is already uploaded in your Google Drive. So what you have to do, go through the main study material link, same Google Drive link, and you see there is a folder on motors. So if you open that motors, you can see this particular document, motors and speed control. But unfortunately, not much content is there on the speed control, especially not much content is given for the PMSM. But as you know, I have showed you a market survey also. PMSM is the number one choice, right? That is the reason we need to study little more as compared to what study material is provided, right? You will understand what I'm saying as we go along. But then there are some important topics which are already covered in the study material. So the strategy we are going to follow is we are going to follow important content of this particular study material which IntelliPART team has already provided. And then we are going to learn additional things, especially about PMSM, right? Why? Obvious reason, PMSM is the number one choice, right? Worldwide, four-wheeler segment. So let us quickly begin with motor and speed control method. In case you did not understood some of the power electronic concept, that is absolutely okay. Today we are starting a new topic, okay? And we are also going to solve some problems. So I would request that you get ready with a pen and paper and maybe a basic calculator, all right? A scientific calculator, regular one will be sufficient. So what are the topic today that we are going to discuss mainly? The subtopics rather. First, we are going to understand what is an electric motor. And in electric motor, there are different categories, okay? DC motor, then brushless DC motor, permanent magnet DC motor, induction machine, switch reluctance motor, then comparison of motors, and then force calculation for motor selection, okay? This is going to be very important that we are going to spend a lot of time on this. We are going to spend some time on DC motor, some time on induction machine, but as you can see in the study material there is no PMSM. That's the reason I'm saying that for the material because we need that. And brushless DC motor, this is mainly used in very light duty EVs. So if time permits, we are going to also follow. We are going to study it. So for BLDC, again, I have provided you some simple study materials, one PDF of the book, some explanation about BLDC, and I have provided you a MATLAB simulation file also, how we control BLDC motor, those segments, okay? So if time permits, kindly go through them. I'll also give you some introduction about them. So let us begin with what is an electric motor. So electric motor is a device which takes electrical power as input and provides mechanical output, right? So in general, we say electric machine is the common terminology, okay? And electrical machine. Okay, that is the generic terminology that we use. So when someone say electric machines, it has two category. Okay, one we call it motor, another we call it generator. Now, do note, a single machine, it can act as a motor, it can also act as a generator. Okay, same device. So for example, in electric vehicle we use PMSM, right? So this PMSM, when you are driving the vehicle, right, you want to go from point A to point B, you are actually using this motor in motoring mode itself. Okay, or in other sense, that electrical machine is acting as a motor, the same device. But when you are applying a brake, right, electric vehicle has a feature that when you apply electric brake or you apply mechanical brake, some of the kinetic energy of the vehicle can be converted back into electrical energy, and you can utilize it to charge the battery little bit, right? So when you do that, we call it regenerative braking, right? During regenerative braking, this motor or this electrical machines, it acts as a generator. So there is a beautiful example of same electrical machine. You are working it as a motor sometime, as a generator sometime. When as a motor? When you are driving the vehicle. When as a generator? When you are applying a brake. Okay. This happens in electric vehicle, of course, not in IC engine vehicles. So what is the definition of a motor? Or what does it do? So a motor is a device which takes power input, P for power here. The power input given is in electrical form. And the power output we take, or in general, the output we take, that is in mechanical form. So input given is electrical, the output is taken as mechanical, that is a motor. And what is a generator? The opposite. So generator is a device which takes mechanical input and it gives you electrical output. Okay, same device. Now, when someone say electrical input, what we mean is we apply voltage, we apply current, right, to the motor, and as the output what we get is basically torque and speed. That is what in mechanical domain, right? So now, in a motor, we are going to concentrate mostly on the motor because most of the time the vehicle we apply electrical energy and we get mechanical output. So first, let us talk about the input section, right? Input, electrical input, we know it can have DC, it can have AC, right? And then there is a category called universal. That means it can have both AC and DC. So when you apply DC to a motor or a motor which needs DC power supply, we call it DC motor. Which needs AC power supply, we call it AC motor. And universal motor is which can operate both on DC as well as AC. So broad category wise, three type of motor: DC motor, AC motor, and universal, that is DC as well as AC motor. Okay. In electric vehicle, Generally, AC motors are used. Most popular are PMSM, you have BLDC, you have induction machine, you have SYRM, synchronous reluctance machine. Okay, these are the most popular ones. Okay, now majority of the electric vehicles which are running on market or worldwide, they are mainly AC motors, right? So in AC, and you see these are mostly three-phase motors. This we need to remember, right? Now in AC, what are the important parameters to understand? One is voltage, and one is current. Then we have frequency, we have phase, and we have power factor also. And there comes harmonics. These are the important parameters we need to understand. Okay, we'll take slowly. So AC, as I told, we need to understand what voltage. Voltage more or less everyone knows. Current is also familiar to all of you more or less. Frequency is also okay. We are going to revise them, not to worry. Phase, power factor, and then this power also in general. Okay, so let's understand a little bit about them so that our concepts are clear. So a voltage source AC is shown by this segment, this symbol. Basically this kind of symbol, right? It is 0 volt here, then we have positive voltage, and this side we have negative. Typically we always apply sinusoidal voltage, or we want to apply sinusoidal voltage. So generally we want sinusoidal voltage. For example, the voltage supply you have in your home, that is a sinusoidal voltage. How do we write it? We write it Vm sine omega t. Okay, so let us understand. And then plus minus phi, that is a generic form, volt. So any sinusoidal voltage are generally written in this form, Vm sine omega t plus phi. Okay, let's understand each of them individually. What is this number signifies, or this variable signifies? So if I plot this particular signal over, let's say, time, or we can also sometimes we do it over angle. So for time being, let us make it very simple. So if we draw this waveform, it will look something like this. Okay, so it is a sinusoidal voltage. Basically it is a voltage, every instant of time it is changing its amplitude in a sinusoidal fashion. This line corresponds to 0 volt, this x-axis. Okay, this peak value, this is known as Vm. That means it is the maximum amplitude. Okay, and this particular waveform, it is one positive half cycle, one negative half cycle, and then it repeats itself. It is a periodic signal. So this time period is T. Again for next cycle, it will be T. So what is T? T is the time period. And as you know, frequency, that means number of cycles per second, is given by 1 by T. Unit of frequency is Hertz, Hz. Time period unit is seconds. Alright. Now, there is a term you see, omega. Omega is known as angular frequency. It is given in the unit of radian per second. So this omega is nothing but 2 pi f. Okay. So this is 2 pi f omega. F is in frequency in hertz, whereas omega is in radian per second. Now, t is of course unit of time, indicates time in seconds. And then you can see there is another part, phi. What is phi? So here in this particular waveform, you can see if I say my time equal to 0 here. Okay, so in that case, this phi will become 0. It has no phase. Okay, it starts exactly at 0. So phi is 0 degree. Let's take an example to make this concept of phi more clear. Okay. So now if I connect a load to this AC system, say a fan, a ceiling fan you have in your home, ceiling fans, right? Typically, if you connect AC voltage source to a ceiling fan, which is a single phase induction machine basically, you will see that if this is your voltage waveform, your current waveform may look something like this. So what is happening is your voltage waveform starts at t equal to 0, but then you can see your current waveform starts after some angle. So typically, one complete cycle in radian per second, right, or in general in degree, sorry, that is 360 degree. One complete cycle. So that means one half cycle is 180 degree. Okay. So now that current waveform, it starts after some time. So this angle is known as that phi. If I assume this current has an amplitude Im, so this current expressions, we are going to write it like this: Im sine omega t plus phi 1. In general, let me call it phi 1. That difference between, so basically you can see the current waveform started slightly after the voltage waveform. So we call it the current waveform is lagging the voltage waveform. It happens mainly in inductive kind of load. Okay, most of our loads are inductive in nature. The motors that we are going to study, right, for electric vehicles, these are mostly example of inductive load. When I say inductive load, it can be a combination of RLC or it can be a combination of RL mostly. Okay, basically there will be some resistive part, some inductive part. Inductive part is more than the capacitive part. That is the meaning of inductive load. So in that case, current lags the voltage by an angle phi. Okay, this phi can be different values depending on your type of motor, operating condition of the motor. So what I'm trying to say is very simple. Your voltage waveform and current waveform, there will be having some lag in most of the motors. Okay, so that angle, let us say phi. So this angle phi is known as phase difference, which is very, very important to understand. Okay, so I hope you understood voltage. Current is of course voltage by your impedance or the resistance part, if it is a purely resistive load. So let us quickly revise one more time. This voltage, how did we write in general? Let's say Vm sine omega t. I am assuming it is starting at 0 instant. Okay, so that's why it is having no phase difference. It is starting with 0 itself. This is the load. Its impedance, say Z. Now you can say what is impedance. For a DC circuit, we studied resistance, right? For AC circuit, we are going to have some inductance, we are going to have some capacitance. So the total opposition offered to the voltage by the circuit elements, it will be opposition offered by resistance as well as inductance as well as capacitance, right? So their combined opposition, that is known as Z, which is impedance. Its unit is ohm. Okay. So current in the circuit I is going to be V by Z. Okay, V is the voltage, Z is the impedance. So if this is your voltage, and say this is your current, voltage we are going to write Vm sin omega t, current we are going to write